So let's see the same example that we have seen earlier. So we have a program. Let's say this is some hello.c program. When we compile this program, it will generate an executable file. And once we run this particular executable file into the shell, so that exec will be called to that particular program. Let's say it is there hello.c, and the object file will be created for that. So that file will come here, and it is going to be the part of the process right now. Okay. So once it will be the part of the process, in the virtual memory space map is there. So one part is the text part where all the instruction will be there. There is a data part where we are going to put the global and static data of the program. There is a heap part and stack part. These heap and stack part are not the fixed memory location. It is going to vary. The heap is going to, we are going to put into the heap some system call, some functions which is going to be useful in the runtime. Means let's say malloc and calloc if we have. So we'll put that particular instruction here. Then we have a stack. Inside the stack, we are going to put the recursive functions, different functions and its arguments that will put into the stack. Okay, so this is the virtual memory space for any process. Up to the maximum size that will go, and the maximum size is different in x86 type of operating system and your Unix based operating system. So that we have seen earlier in the example. Okay. So the same thing will be depicted here. Let's say we have this particular process, and this process into the virtual address. So let's say we have a process P1, let's say. So this process P1 has a part from 0 to maximum size, and all these parts are in the form of blocks. Okay, and we'll put into the form of blocks. So this is 1 block, 2 block, 3 block, 4, and we have, let's say, 6 number of blocks to accommodate the data and those global data, those functions, those malloc function, all those things will be there in the number of blocks. Now, how to map this particular process into the RAM or into the main memory? So what will happen is the blocks or the pages which is there in the RAM is called page frame, and these addresses is called page frame addresses. And here we have block addresses because all are there in the form of blocks. Eventually the block size and the frame size are the same. Let's say it is of 4 byte. So the block size here in the virtual memory space and the frame size here into the main physical memory space, the size is the same. Okay, but we have to map it because the RAM size is depend upon whatever the your RAM size is, 4 GB, 8 GB RAM size. So it varies. So here the memory space, as I told you, the frame is divided into, previously we have talked about word, right? So every a chunk of instructions are in the form of a word. So that word has, sometime we call as a page, or we can say it is a page frame. Here we talk about page frame. Okay, so the block size and the page frame size are the same. Now here we have a process page table. So each process is attached with a process page table. Okay, and this particular process page table is nothing but a mapping between block and the frame. So where the first block data is, the first block data is there in the sixth frame. So where is the sixth frame? This is the sixth frame where we have the first block of data. Now the second block of data is in the 13th frame. So it is in the 13th frame. Third block of data in the 9th frame. Third block of data in the 9th frame. In that way, we do the mapping into the physical memory space. So you can say this is called physical and this is called virtual address. This is a physical address. This is a virtual address. Physical address is there in the main memory, and virtual address is there. We are storing into the secondary memory. Okay, because it is virtually summed. So we can say it is in the main memory. Sorry, secondary memory. So virtual is in the secondary memory. Now here also it is reflecting the same way, but if, as I told you, we have the part in the virtual address, we have the part, this is your user space or user part, and the whole space is your, from here to here is your kernel space. So because kernel is also the part of each process, means each process will be having the kernel part. So the kernel part is also there. So how we are going to map here is in that way only. So we have this particular virtual memory space has a process page table in which the kernel process and the user process is we are putting here, and we are putting the page frame here, and this page frame we are actually mapping. So you see, these are the kernel part, which is there in the this particular kernel part which we are putting into the main memory, and that there is a process, and these are the processes part which are there into the main memory. Always remember that in the main memory, the kernel process will be there in one portion, or one consecutive memory, or one consecutive page frame will be allocated for the kernel. Okay, there is a significance of that. We'll see it later on. What is the significance? So I think you understood that what is the use of this page table, because this page table is for the mapping. It will do the mapping between virtual address space and physical address space. Okay, physical address space is your actual main memory where we are going to store, and virtual address space is attached with every process, so it is stored in somewhere in the secondary memory. Why we need this particular mapping? So if I want to use that particular program and I want to execute that particular program, and I'll put that particular program into the main memory, so I have to use this particular table so that I can put the block into the main memory. Okay. So as it is there, like we have this particular kernel space. This is your kernel part. Here also this is our kernel part, and the user space where we have the user program. Here we have some user program into the main memory. So as we have discussed that for the kernel, we have some consecutive part that will be allocated of the RAM, and we'll put the initial part of the RAM or initial part of the frame of the RAM will be allocated to the kernel. So that is very much essential. What is the reason behind it is to map between virtual address to physical address. It is very much easier if we'll do like that. So how it will be? Let's say the virtual address of a particular block is this. Okay, and the physical address of a particular block is this. So what we do is, how we'll get from virtual address to the physical address, we'll just subtract the maximum size. This is the maximum size in the XVC operating system. So that particular maximum size will be subtracted from the virtual address space to get the physical address space. That will be minus with the maximum size. With the maximum size that we have done. So if this is the virtual address space, we'll just minus it with this particular value, we'll get that particular value. This is the physical address space. To make it easy to convert, what we do is a virtual address space to the physical address space, we subtract the maximum size. And if we want to convert the physical memory, physical address to the virtual address space, we just have to add maximum size. So it will be very relevant when we do that like that. Okay. Now let's talk about if we have multiple processes. Okay. So we assume that this is process P1 and this is process P2. This is the user space of process P1 and this is the user space of process P2. So as I have already told you that there is a virtual address space for each and every processes. So this is a virtual address for process P1. This is the virtual address space for process P2. But here you can see the kernel part are the same, right? Kernel part are the same. So what we'll do is we'll not going to put the kernel part as a separate way. We'll put the kernel part because it is the same. So we have to put only one copy of the kernel part. And this is the one copy of the kernel part. For this is the process table for process 1 and this is the process table for process 2. So you see that how it is mapping from the virtual address space to the physical address state. Here also from the virtual address space to the physical address space, and this is the RAM. Here you can say this is the part of P2 and this is the part of P1. Right? So the P1 is also there, P2 is also there, and the kernel part is there. So because the operating system part will be the same for all the processes, but in the virtual address space, it is there in a separate, but they are the same. That's why we are putting together and we are putting into the lower part of the RAM. Okay. This is the same that we have seen in this particular example. Now kernel data about the process. Now what is the kernel data is used about the process. Now in the main memory, let's say we have different process. Let's say this is P1, this is P2, this is P3. So for related to the process, what are the metadata that we have to use or we have to store other than the program? We have the program or the part of the program, which is there, the text, and then we have data, we have stack, and we have heap part. Apart from that, what are the other things that we have to put into the main memory for the kernel usage? So we know that what are those? We have the process control block, which is all the attribute related to the process. That is also be there. We have page table for the user. The page table just now we have seen, that is also there. And we have the kernel stack of the user process. That is very much essential. And this is, we are putting into the kernel space. Okay. So all these three things are the metadata. Metadata means the data is there, means the actual program is there, but about the program or about that particular process, there are different things that is there that is called metadata. So you can see here, all these are different metadata that will use related to the process for the further processing or further usage in main memory. So we know what is process control block. We have already seen, right? We should have process ID, its state, its priority, its open file, its closed file, its open devices, its closed devices, the general purpose registers. All those things are the part of the PCB, process control block, which is also called process attribute, which is also called context, right? Page table, just now we have seen page table is nothing but is a mapping table between the virtual address space and physical address space. And this particular kernel stack of the user process, that will see that what is the kernel state and what is the usefulness of this particular stack, which is called kernel stack. It is in the part of the kernel, but it is related to a process. That's why we need this particular kernel part, and this particular kernel part is required to the each process, because here we are going to put kernel stack of that process. So related to that process, there is some stack that we have to put into the kernel. And what is the significance and what is the use of that, that we'll see slowly later on. Now what happened is, just now we have seen that there is these all the metadata and all those things are there, and the data related to it is there. We have the stack part, right? Here also in the kernel part also we have a stack, and this particular stack is related to that process only. So if this particular, you can say this particular stack is related to P1, so this is your P1, okay, process 1. If we have process 2, then there is another stack which is for process P2, if we have some more processes here. Getting it? So each process has two stacks, user space stack and kernel space stack. What is the use of user stack space? User stack, we know that in the stack we'll put the recursive functions, we'll put the functions data, and we'll put the argument of the functions and all other related data here. In the kernel space stack, what we are going to put? So it is used when kernel code in the context of a process. Now when it will be useful? It will be useful when the process is going to be executed into the CPU, and then from the CPU it is coming back into the main memory. You know that what is the main memory? It is a ready queue. So from the ready queue or the ready state, if a process will go to the CPU, or from the CPU the process will again come to the ready queue. So for that purpose, that stack will be useful. So when we do the system call like execute it, so at that particular time we actually required this particular kernel stack, and this particular kernel stack is the kernel code of the context of a process. So context means there are many things that will be there, such as we'll put some register value, we'll put the process program counter, some general purpose register or CPU registers we are going to put, and we are going to put the state. All those things are there, and your open file, open files, close files, or open IO devices. All those things are the part of the kernel stack. Okay. Kernel can execute even if user stack is corrupted. So here, if the user stack, this particular user stack is going to be corrupted, so then also that process is going to run through the kernel stack. Okay, so that is a use of this particular kernel stack. So attack that target the stack, such as buffer overflow attack, will not be affected the kernel, because if we'll do the buffer overflow, I told you that what is the maximum size of any uh, virtual space, right? So the maximum size is this one. Let's say if we are beyond that particular size, so that is called memory overflow or the buffer overflow. At that particular time, that program will be corrupted because we are not going to put the program into the kernel space. At that particular time also, the kernel space stack is going to be useful for this particular purpose.